And then you can go in and look at it and zoom on the cloud there. You go back into the same invitation on ones that are completed, and you can click on it. Um, I'm going to also work on putting these. I've put the first two in um, YouTube as well, but I think for the most part, you can just go to the cloud and see them. All right. So here was the mean. It's got a fancy looking formula, but all this little thing up here just means that little thing right there, Greek sigma, just means the summation of all the x values, and then divide by n, which is the number of x values. So here was the data set we had: 78, 83, 92, 68, and 85. In the numerator, add them up, it's 406. And then there are 5 pieces of data, so you divide by 5. And so your mean score is 81.2. Notice they go out with these calculations 1 decimal place past what the original data was. That's generally good practice, unless they tell you different. Sometimes they may tell you to round off, so you got to watch out. All right. So the median is essentially the middle of a data set. All right. So if you've got some numbers lined up, you're going to have one or two situations. Either you're going to have an odd number of pieces of data, which is going to make this incredibly easy, because once the data is sorted highest and lowest to highest, then there'll be exactly one data value in the middle, and you can go and find it. See how, if there's an odd number of pieces of data. So this is 7 pieces of data. I'm sorry. 7 pieces of data, so there's 3 on the left and 3 on the right. Now, if you got an even number of pieces of data, well, you got to create a mean. So that just means taking the 2 middle ones. This is 8 of them. So there's not 1, but there's 2 in the middle. So we're going to just take the mean, or the average, of those 2 middle values. So, as I said, the first thing in order to find the median is to sort the data lowest to highest. See, here's the data that we had, but sorted, it looks like this: 68, 78, 83, 85, and 92. Now, since there's 5 pieces of data, then there's exactly 1 in the middle. So that's the median. It's that simple on the odd pieces of data. Now, if you got a lot of pieces of data, there you can even use a formula for that. I do believe that Alex will show you that. But for the most part, I don't think you're going to get into any really large data sets and have to worry about it. Because if you got a real data set, then you can use something like a spreadsheet to find the median for you. All right, so 8 patients undergo a new surgical procedure, and the number of days spent in recovery for each is as follows. So we got 8 pieces of data, but we're still going to sort them. So the lowest was 12, then 13, another 13, a 15, a 19, 20, 21, and 27. So this is them sorted. Now, since there's an even number of pieces of data, there's 4 on this side and 4 on that side. There's not 1 data value in the middle. There are 2 pieces of data in the middle. So then what do? We add these up, and we essentially create a median that's exactly halfway in between 15 and 19, which is 17. And you can kind of see it. If you were counting by ones, it would be 16, 17, 18, and 19. 17 is right in the middle. All right, we all right on that? Any questions? Don't ever be afraid to ask anything. I have a certain amount of things to go over, but for the most part, as long as we're actually accomplishing something in regards to learning, that's what the class time is for. Now, You can use the calculator, and it actually will also do the next calculation as well, called the mode. But once you put your data in that array that we talked about last time, and this is for the TI-84 Plus, you can click on that. There's a probability button on there. So if you click on this, is it that? Yeah, there it is. So this is where you put the data in on the very first one when you come into. But for all this var stats, you go over one to calc, and then you hit enter. Now I don't have anything in here, any data in there, which is why, but let me go ahead and show you. Now, I'm gonna go ahead and put those in there since it's a small data set to just show you. What's going on? All right, this is it. So just hang on if you want to see this. So I'm gonna put the data in, do everything, go to stat, hit enter, and then just put these in. 68, enter. 78, enter. 83, enter. 85, enter. Now Alex has its own little built-in calculator. And it may do some of this, so you may get some instructions. So you're free to use that, because since that one's built into the Alex system, then when you test, you know it's going to be there. The one drawback is the tests, or at least the major tests, the exam and the midterm, are going to be with that lockdown browser, so you're not going to be able to run the one of these that I got in Canvas. Now you can, as long as you declare when you come in, you can actually put this on an Android phone, as I showed you that I got. And I got no problem with that for this class. So it's that same thing that's in Canvas, and it looks exactly like the one that we're dealing with on the phone. Because I hate to have people go out and spend $100 on something if you don't really need it. Now, to do the calculations, you come back to stat, and then go over one to calc, and then hit enter. See, that's that what they show you right here. All right. Now, I'll actually show you the whole procedure right there that I showed you. But all of these things right here, this is everything that you're going to have to calculate in chapter 3. You've got at the top the X bar, which is the mean. These two next to the second and third one, I don't know why you would need those. We're going to talk about this next, the sample standard deviation and the population standard deviation. And then on down here, you got what's called the 5-number summary, which is the third part of chapter 3. So this does everything in chapter 3 for you in one click. All right, so we already looked at those. So see, like I said, is you get both of those things. Let's see. I guess you don't get the mode. I thought you do, but doesn't matter, because this book really doesn't that big on the mode. All right, so now what we want to talk about here is just a comparison about the differences between the mean and the median. The reason why these are both measures of center, as well as this guy that does this book doesn't believe the mode is a measure of center. But if the data is normally distributed In other words, it's symmetric, then it is the measure of center. But we want to compare these two two measures of center, the mean and the median, and see the difference between them. Because why do we need two of them? Well, first of all, the median is what we call resistant, and the mean is not resistant. So what that essentially means is that when we calculate a mean, and you all know about this because if you had 5 test scores and 4 of them were, in the 80s range, and then one of them you had a bad day and it was a 20 something, that when you add up all 5 of those grades and divide by 5, that low grade skews the data down. So instead of having a B, you would probably, might be lucky to have a C. So that's the reason here. The median is not affected by extreme values, whereas the mean is. All right, now this is an example of you got 5 families that have annual incomes of 25,000, 31,000, 34,000, 38,000. No, I'm sorry, not 38,000. 34,000, 44,000, and 56,000. All right. Now we're going to have one family, and it's the ones that's making the lowest of $25,000. They win $1 million lottery, so their income increases to $1,025,000. So what we're going to do is just show the mean and the median for each of these. So the mean, if you were to add all these up, we'll go ahead and do it here, just so you can see. Nothing up her sleeve. So we got 190 divided by 5, and that's where the 38,000 for the mean comes. Now I'm just going to show you here. All right, I'm just going to separate these for a minute so you can see, since they're already ordered. So there's 1, 2, 3, 4, 5. So the one in the middle is the 34,000, and so that's where this comes from. So as the salaries stand without that windfall of $1 million, the mean is 38,000 and the median is 34,000. Now, let's say after the lottery win, we want to find out what the mean is. Well, what I'm going to do is I'm going to replace this one with that. And still got 5 of them, so what happens?
The median stays the same.
Well, before you say that, I want you to watch something.
Okay.
It almost does.
No, it don't. Okay.
It's because of the order.
Yep. I just saw it.
Okay, so now the sum of all of them is that. So let's say divide by 5. So now, see, it's 238,000 is the mean. It jumped up by $200,000. So one extreme value can skew the mean either up or down. This one's skewed up because in actuality, it's up here. So I'm ordering them down again because in order to do the median, I got to order them highest to lowest. So now there's no longer that 34,000 in the middle because that one that was way down here that was the lowest before is now the highest. So the median is 44,000. But look how much it changed. How much did it change by? The mean changed by $200,000. We had to add a whole decimal place. But the median only changed by by $10,000. See, that's what we mean by resistant. That big windfall did not affect the median. So depending on the type of data, the median will give a better, it gives a visual center to the data, whereas the mean gives a numeric center. I'm going to put all this back the way it was. Okay. So that's what we mean by resistant. Now, on normally distributed, I'm sorry, what we did at this point, they don't call it normally distributed. They call it approximately symmetric. All right. So the data that's spread out like this, and when we see, the reason why we know this is because generally we're looking at a histogram to be able to tell whether it's more or less that shape. But on that type of data, the mean and the median are more or less equal. But on data that's skewed to the right, which is very similar to what we just had, the mean gets skewed, pulled to that right side. Remember that $200,000? Probably this one would be skewed even more than this because our mean would be pulled way over here. You remember it was 200,000, 234,000, I think it was. But yet the median doesn't pull nearly as much. Same thing, if we had a real small value on a data set, then it gets skewed to the left. And then the mean is going to be less than the mean because an extremely small value will skew your data down. All right, any questions? I need to get me some water here. So any questions? Okay. Let's go on and move ahead. Now, the mode of a data set is another a measure of center. So it's when the data is normally distributed, then it is. This guy right here doesn't believe that the mode is a measure of center, but that's one of the things about statistics is it's not like something like algebra that's all been standardized. Just in statistics is changing as we speak, so to speak. All right, so what the mode is, it's the piece of data that appears most often, most frequently. And then you could have one of three scenarios. You can either have zero mode. So if you have all unique data, then there is no mode. And then if two or more values are tied for the most frequent, then you can consider those all modes. So you can have more than one mode, no mode, or one mode. Now, generally, if you've got that symmetric data, then the mode will be right in the center with the mean and the median, and you'll have just one of them. But let's just look at this. Um, 10 students were asked how many siblings they had. I actually made a change on one of these. Oh, okay. I know what I did. So 0, 1, 1, 1, 1. So we got 4 ones there. We got 2 twos, we got 2 threes, and we got a 6. So which one appears the most? It's the 1 because it appears the most. It appears more than any other of the values. All right, now these other ones are ones that I made up just to kind of make sure we understand these differences. But what I did here is I put in a couple of extra 2s so that we have a tie. We got 1, 2, 3, 4 ones, and we have 1, 2, 3, 4 2s. Nothing else is even in the contention. It's just a tie race between those two. So 1 and 2 are the modes here. Now, if you have data that's unique, in other words, look at this. Is there anything that's repeating? No, there's not. So then we have no mode because each one of the data pieces are unique. This is why and not because it is, I don't really quite understand his logic here about why he's saying it's not a measure of center. He said the mode could be the largest value in a data set or the smallest value in the data set or anywhere in between. And that's true. But you remember that example that we saw over here with the mean and the median, I mean, the median and the, hold on a second, everything's like all of a sudden slowed down. See, these aren't equal. The only time it's equal is when the mean is equal to mode. He's showing us a data set that's obviously not normally distributed, but if you have, or not approximately symmetric, but if you got a hump in it right there, then that hump represents the tallest, the value that appears the most often. But anyway, we don't need to get into all that contention. The one thing that is unique about the mode is you can determine the mode for qualitative data. You obviously can't calculate a mean and a median on data that's non-numeric, but with the mode you can. If you have something like this, where you have what was this? This is the cars that were rented on a particular day, and it's just by the make of car. In other words, the that's what we consider a make of a car. So it just shows us all those, and they tell us that the mode is Toyota because Toyota is the one that's in there the most. So you got 1, 2, 3, 4, 5, 6 Toyotas, and you have 2 Nissans, you have 4 Chevrolets, you have 1, 2, 3, 4 Hondas, and then you got Fords. 1, 2, 3 Fords. I'm sorry, 4 Fords. So it's clear that the Toyota is the one that appears most frequently. So that's why it's considered the mode. And when you have non-numeric data, which is also called qualitative data, then you can determine the mode with that. Whereas you wouldn't be able to do that with data. I mean, non-numeric data. There's no way you can calculate a mean and a median here. I'm just going to go over this briefly. This is not major, but it is important because I know they're probably going to have you doing these in there. So let's say you got a frequency distribution. And the thing about a frequency distribution is that it does not show you the original data. That's one of the weaknesses of it. It just tells you how many are in a particular range. Now, if it were qualitative, they might be able to do that. But or even if it were discrete, they could do that. But for this kind of data, where you got the classes, class widths, you know that there's 10 values between 0 and 49, but you don't know how many of each one there are. We just know there's 10 of those in that range, 5 of them in the 50s to 99 range, 13 in the range of 100 to 149, 11 in the range of 150 to 199, and so forth. Now, in order to be able to calculate the mean from data like this, and it's not really, if you were to take the original data and calculate the mean on it and then calculate it like this, it'd probably be going to be close, but that's why they call this an approximation. Approximate the mean. Well, watch what they do. First of all, they find the midpoint of each one of the classes. Midpoint of each one of the classes. How do they do that? Well, they take the endpoints I'm sorry. They take the class width and divide by 2. What's the class width on these? In other words, how many values are there in this first one to start? How many are there in there? How many numbers?
48. 48, huh? Or 49.
So you're not going to count 0?
Oh, 50.
See? Okay. Now, that's why this can be confusing, because that's the first thing that people look at, and they'll just say, oh, there's 49 numbers in there. You know why? Because when you count, you usually don't count 0. You count the second number. All right? You count from 1, and that would be 49. So the way we know for sure what the class width is, and the way that they tell you in here, is you take any 2 upper or lower and you subtract. In other words, 100. Well, let's just look at the first one. 50 minus 0 is 50. 250 minus 200 is 50. So all of these have a class width of 50, and they should all be the same. Now, how did they determine the midpoint? Well, they take that class width of 50 and divide by 2. And that tells us the midpoint of the first class. And then from then on, we just keep adding 50 to get the rest of them. In other words, 25 plus 50 is the second one. 75 plus 50 gives you the next one. And then just keep adding 50 plus 50 plus 50. See that? And that's how they get all those midpoints. Now, what that allows us to do is have a single number to multiply times the frequency inside of there. Essentially, what we're doing is we're kind of just cheating and saying, well, since we don't know what the values are in there individually, we're just going to use the midpoint, like an average again, and then multiply 25 times 10, 75 times 5, and so forth. See that? This was the frequency in the original frequency distribution. These were the midpoints we just came up with, which is just a matter of, for the first one, taking 50, the class width, dividing by 2. And then once we've got that first one there, then just keep adding 50 all the way down until you get your last one done. All right, then you multiply across. So that's 250, 375, 625, 1925, 1575, and 1100. Now that's what they call the frequency times the midpoint. And so when you add all those up, in other words, add up this whole column, you're going to get 6,850. Now, did they ever tell us? I mean, we can add these up, but I was just wondering if we could, yeah, 50 high school students. So if you add all these up, that should be 50, and you take 6,850 and divide it by 50. So this was like the number of texts that students sent throughout the day. So the mean number of texts would be 137. But again, that's an approximation. Now, this technique is going to be useful again in chapter 5. So that's the reason why I go over it. Otherwise, it's not all that important. But this idea of the two columns and multiplying is going to be important later on. All right, any questions before we move on?
Can you back up one, Professor Cruz? I see you. I wrote that you have to subtract the final class, then you divide it by 2.
Mm-hmm.
Okay,
and then keep adding 50 to get all the rest of them. Because remember, all of these are 50 apart.
And what you did to get the frequency?
Well, those are already there. That was given to us.
All right.
See that? The original one?
Oh, okay.
So we're just creating this from a frequency distribution.
Right, okay.
Hold on.
I do have a question, but it's unrelated to the topic at the moment. It's just about the M&Ms.
Oh, yeah, I forgot about that. We'll probably do that
next
Thursday. I'm sorry.
Okay.
Monday then. I forgot about it.
All right.
Because that'll be a good thing. How many people have M&Ms?
I do, but it's just at my house. I'm at school right now.
All right. All right. So for next time, bring it. If you don't have them, then we're not going to be able to do it because I can't really do it. We only got 10 people in here. They're keeping the course small, so in case we go back to school, because we can't bring too many people into a classroom. So it's real hard to do it with that small of a group. So you might have to bring 2, because like I said, if everybody doesn't have them, we're not going to be able to do it, because we need to have probably everybody having a couple of bags now that I think of it. All right. But it's what I can show you is how sampling works with that.
I'm sorry. Are we looking at being on campus for our next class?
No, that I know of. Why? Have you heard anything?
I haven't, but they said that they pushed it back until the first. So, I mean, they haven't pushed it back again that I've seen.
Well, but you got to realize they didn't. They were originally intending this to be on session, so they basically did pushed it back 3 weeks at the very outset. If you ask me, and I'm not, you know, in government, I wouldn't hold my breath about that because look what's happening. They're having all this outbreak from Christmas and even Thanksgiving that's coming to bear now. And they're dealing with that second, what is it, the variants on, I forgot what they call it. There's a variation on the virus, and they're concerned about that. So, like I said, that's just my opinion on that. Because when they first said they were going to have classes on campus, I know I thought they were pushing it too quick, personally, and I was right. But like I said, I might be wrong this time. But it won't be next class because even if they don't push it back, it's not till February, which is still 2 weeks, right? Well, it's past this week. No, wait a minute. It is next week, isn't it?
Yeah.
But I have not heard anything, so we'll just have to see.
Okay, thank you.
Well, thanks for bringing that to mind because I didn't think about it being next week, but you know, I just I have not heard anything. Probably hear something by Friday, and then I'll let you know. All right, so measures of variation now. This is the second part. What was kind of sad about it is that like they were wanting to do the 097s as being, which is like the intermediate algebra, and she had to go in and change them all back because they decided on the 097s that they weren't going to jump back and forth. So they just kind of stacked those out now that they got like 25 or 30 people. So there's no way they're going to be able to bring those. But she, like I said, originally she wasn't going to keep them small. And then they just said, well, we're not going to just go back and forth with those students. But I think it's because they just wanted to put more students in the class too. All right. There are two measures of variation. Two measures of variation. All right. They call it measures of spread or measure of variation. And what that essentially means is, and I'll kind of show you. But I was trying to find one that would be, because that's one of the things they don't have in here is a good illustration for this. But I just wanted to show you. Okay. All right. Let's just kind of look at that left-hand side here In other words, don't pay attention to the green ones. Just look at the blue ones. Measures of variation essentially just tell us how skinny or how fat that curve is. See, so we go from standard deviation of 1 on the first one to 2 on the second one, 3 on the third one, fourth one, and each time it gets more and more spread out. So that's what the standard deviation does, or that's what the measure of variation does. The standard deviation is the second measure of spread we look at. The first one is called the range, and it's really not all that of an important one. It's not one that's used, but I'm just going to kind of show you this. Let's say we've got some temperatures. This is for San Francisco, and it's just the average temperatures throughout the year for a particular month. So in other words, the average monthly temperature in January was 51, in February it was 54, and so forth. So in order to calculate the range, what we do is we take the highest value in the data set and subtract the smallest one. So 63 minus 51 is equal to 12. All right. So as I said, the range is very easy to compute, but it's really not all that useful. It can kind of tell you how spread out things are. You could kind of look at it. Oh, you know what? Let me look at something real quick. I think this is one of the things I have in my notes that's worth looking at for this chapter. Oh, so I said this is one of the things that I have in my notes that thing there. But I'm looking for that. I thought I had an alternative example. Okay, yeah, here. Now let's say we're looking at temperatures for our home region here. So let's say we take the hot, we're just going to look at the red line. And so we're going to find the high temperature, what looks to be about 92, which is, as you might guess, is in July or August, right in there. And then the lowest one looks to be 42, and I'm going to just say that's 42. So then when we subtract, we get a range of 50. All right, how does that compare with San Francisco, which was 12? Well, the range is much higher in Louisiana or in New Orleans. So what that means is there's more variation throughout the year. Whereas in San Francisco, the temperature is a lot more even. Look, they're just in the 50s and 60s here the whole year. Now this is the average. Like I said, they have lows and highs as well. But that just tells you a little bit something. Probably someplace like Hawaii be the same way. There's just not as much variation throughout the year. All right. Now, the way this kind of handles things, the variance in the standard deviation, if you calculate the standard deviation, you have the variance. And essentially the variance is just one step, mainly taking a square root from getting you to the standard deviation. All right. So just keep that in mind. And the standard deviation is by far the most important calculation. They may ask you for the variance in the some of the homework, but like I said, is for the most part the standard deviation is more useful. So this is just basically selling the same thing. When there's a small amount of spread, like in the San Francisco temperatures, the values are closer to the mean, closer to the mean. Whereas if you have a larger data set, they're more spread out. Now, this the variance is just a measure of how far the values in the data are from the mean. That's all it is. And you just got to realize this, that both for the sample and the population, and this is one of the few things where we have a difference in calculation, there's one slight difference, as we're going to see. All right. So the population variance looks like this. And again, all this thing right here means is sum them up. So what we're essentially doing is we're taking the difference between each data value and the mean of that same data set and squaring them. So however many pieces of data you have, you're going to have that many values squared, and then you sum them all up, and that's what makes up your numerator. And then you divide by n. Now, the standard deviation is just one step further. All right, where were we at? Standard deviation is just one step further from that. So when you take the square root of whatever this value is on the right, you've got the standard deviation. All right, so let's just look at how this works. And most all of it is the same for both population and sample. There's just one slight little difference when we get towards the end. All right, so first of all, you got to have the mean. So they calculate that mean for us. If we add all those up, those temperatures up, it's 690 and divide by 12, it'd be 57.5. All right. Now, we take 57.5 and subtract it from each one, and I'll show you on a few of them so you can see how they come up with them. Take 51. And then that's why you got negative 6.5 there. 54. Negative 3.5. You're going to have some of these negative and some are positive. So for someone like 58, since it's larger than the mean, it's 0.5. All right. So that's how those all come about. Notice that some of them are negative and some of them are positive. That's perfectly normal. And you know what's going to happen? And this is a checkpoint for you, because if you did the calculation of the mean correctly and you did all these subtractions correctly, watch what happens. I'm going to add up all the negative values. So negative 18 are all the negative ones. All right, let's add up all the positive ones. 0.5 plus 2.5 plus 3.5 plus 5.5 . Well, what did I do wrong? Let's go back and check. It should that should be the same. It's just opposite sign. I might have messed up on the first one. Oh, let's see. $6.5, 3.5, 2.5. I think I didn't. Let me go ahead and start over. I think I left out one. I'm just adding them as positive, and then I'm going to change the sign since that'll be easier. Oops. $1.5. Okay. All right. So I need to add all of these right here and hopefully get those right this time. Well, what did I do wrong? Y'all try adding them up too, because I'm.
I did it. I did it already. Are you catching the negative 5.5 at the end?
Otherwise, I'm going to do it on my own.
Can you hear me, Professor?
Yeah, I'm hearing you.
Yeah, I did it already.
On the calculator that I'm used to.
Yeah,
They're adding up?
Yeah, they add up 19.5, negative 19.5, and then positive 19.5. I think you're forgetting the negative 5.5 on the end to the right.
Well, I thought I did it. Let me go ahead and do it one more time. I don't really like that calculator. I don't like punching on a screen like that. So negative point, yeah. So negative 19.5, and then on the other ones it's 0.5, 2.5, another 2.5, a 3.5, and a 5.5, 4.5, 0.5. Yeah. And see, so of course it's not very clear, but it's negative 19.5 and 19.5. When you add those, you're going to get 0. All right. So that's just a test point, a checkpoint where you can just know that you're on the right track. If you've got, they should always add up to be 0, because remember, the mean is in the middle, so they'll be equally balanced on either side of the mean. All right. Now, what you got to do is square each one of those. So when you square negative 6.5, and it doesn't matter whether you square a negative number or a positive number, you're always going to have a positive number. A square is always positive because 2 negatives give you a positive. So when you square each one of these, there's the values you get right there along that top. I mean, the blue row. So add them all up. That's what that whole thing in the numerator bit, right? See that right there? So all of these add up to 169, and it goes in the numerator. Now, here's where the one step is going to be different when we deal with a sample. And we're not dealing with sample here because this is all 12 months kind of thing. So you just use however many pieces of data you had, which was 12. 169 divided by 12. So the variance is 14.083. Now, as I said, the standard deviation is just one more step. All right. So they don't show you this one, I don't think. Yeah, they do. There it is. So for that San Francisco stuff, remember we have the variance of 14.083. So to find the standard deviation, which like I said this is a lot more useful calculation. We just take the square root of the 14.083 and there's our standard deviation. Okay, there's our standard deviation. All right, now let's go back and look at sample. The sample variance / standard deviation is slightly different. And hopefully you can see that in the denominator, you divide by n minus 1. Now, without getting too deeply into why this is the case for a sample, it's just because as the sample size keeps getting larger, so if you have a sample that's small, which they're going to have here, you're going to have a small sample because that's just the way homework problems are, then that difference of 1 less makes more difference and you're erring on the side of caution. But as the sample gets larger and larger, that little less 1 and it makes less difference because the sample is larger. Larger sample fixes most things in life with statistics. But that's the only difference is at n minus 1. It's the same procedure. And they're going to tell you what they think about the n minus 1 if you want to read it. All right, so here we got a sample. Now look at why we know it's a sample. It says a company manufactures batteries. That manufactures batteries is going to test a new type of battery designed for laptop computers. They measure the lifetimes in hours of 6 batteries. In other words, they produced them and they went and pulled 6 of them out at random to have a random sample. So this was the lifetime of each battery. So, and they even say, find the sample variance. So that's how we know to divide by n minus 1. Well, first of all, we got to have the mean. That doesn't change. The mean is the same for the sample and the population. So we just add them all up, add up all 6 of those values. You get 24 divided by 6. So the mean is 4. Now, they're showing you here how Alex shows you. I don't like this. I would much rather use like doing it like this. Actually, I would rather do it, put my values as a column and then have columns, but that's neither here nor there. So anyway, where am I at? So now they're going to take the difference. In other words, they're subtracting 4 from each one of these. 4 from 3 is going to be negative 1. 4 from 4 is going to be 0 there. 6 from 4, 6 take away 4 is 2. 5 take away 4 is going to be a 1. Another 0. 4 minus 4 is 0. And 2 minus 4, you're going to have a negative 2 there. Now, once you square those, they add up to 10. All right. And now here's where the difference is for the sample. And this is the main thing I want to show you in this lesson versus the temperature thing, the San Francisco temperature thing. Because this is a sample, we reduce to n minus 1 in the denominator. So we're not dividing by 6 like we were with the population. We're dividing by 5. And 10 divided by 5 is 2. All right. Now, finding the standard deviation is one more step, and it's the exact same thing no matter whether it's for the population or the sample. It's just taking the square root. So the square root of 2 means that the standard deviation is, or the sample standard deviation is 1.414. I had a student was was contacting me and was asking about the standard deviation. This was for an online class for a more intense kind of thing, and they had went through and calculated the standard deviation, and they were wondering why it wasn't coming out right with something that they were looking at. And I said, well, because you're using the sample standard deviation. The one that you use most likely all the time when you're doing statistics is 1.414. Now, since the book is trying to teach you the difference, they'll throw in a population once in a while. So watch what you get. All right? Watch the wording. Now, back to this calculator. And maybe I'll even show you on here. See, this is the same thing. S of X is the sample standard deviation, and that's sigma, baby sigma. Sigma X is the population standard deviation. Since the calculator does not know which one you're using, it gives you both of them. All right. Any questions about anything? All right. So did Camellia come in? I don't even see less. No, wait a minute. So Camellia didn't come in. What about Justin? Justin Gilbert. Did he come in? I didn't see him. And then Christian Williams. He's been here the last couple of days. All right. So that's 7 people today. All right. So that's probably a good place to stop for now. But this one actually, the standard deviation is also not resistant. Whereas an extreme value will pull it in one direction or the other. So that's just in case you asked that. You can also the same thing with the group data for the standard deviation. You're just going to go out one more point. You take that mean that was calculated, which was it was 137. So subtract 137 from each one of the midpoints, and you got these half negative and half positive. And then you multiply these times the frequency instead. And then that's going to be your numerator, the sum of all those frequencies. And then that's the sum of the plain old frequencies at the bottom, -1, since this was a sample. So it's being divided by 49. Same procedure. It's just that you got to create that those values there by taking the difference between the midpoint and the mean and frequency. And you can even have the calculator do these for you. And this will be handy in chapter 5, because we'll come back to doing this with something else. But you can put the 2 columns in and it'll calculate the mean and standard deviation. Well, let's calculate everything for you. You just got to remember it was a sample standard deviation. 77. See that? 77.3. All right, so that's probably a good thing. Well, let me just mention this real quick. Well, I'll tell you what, we'll remember that we were here. But this is just approximately symmetric data. And what we're going to be able to do when we know data is approximately symmetric, we can assume certain things. And then we'll start talking about the empirical rule when we come back. And that's almost all of this section. Then we'll get into the rest of the 3rd section. All right. So I didn't realize I kind of got carried away. It's almost in the class.